this video, I will introduce you to optimized local I/O ESD protection for SerDes in advanced technology. This presentation will have the following outline. We start by looking at why high-speed SerDes interfaces realized in advanced technology nodes need custom ESD protection. Next, we cover reasons why the traditional ESD protection solutions are not good enough in advanced technology nodes. Following this, we introduce the local ESD protection scheme and then move on to specific examples where it is used to protect SerDes interfaces. We wrap up the presentation with a conclusion. There are three main reasons why high-speed SerDes interfaces need custom ESD protection. First, SerDes interfaces cannot tolerate a lot of parasitics. There is no ESD resistance allowed in the pad, and ultra-low parasitic capacitance is required. Second, SerDes interfaces are frequently operated at low voltage, below standard I/O levels. Third, high-speed SerDes are built on the most advanced process technology nodes, using thin oxide transistors. These thin oxide transistors are easily damaged under ESD stress, as seen in the next slide. High-speed circuits use thin oxide transistors. Compared to more mature technology nodes, advanced CMOS and FinFET nodes have a decreased maximum voltage. As such, we have a reduced ESD design window for advanced CMOS and FinFET technology nodes. Traditional ESD solutions which work for mature technology nodes are not applicable to advanced CMOS and FinFET nodes. For example, in 16 nanometer FinFET technology, core NMOS and PMOS transistors do not survive snapback and cannot be used as ESD clamps. The I/O NMOS and PMOS transistors are also unable to survive snapback and fail at 4.5 volts. They cannot be used as ESD clamps and also cannot be made self-protective. The traditional solutions are not good enough for these problems. For example, a MOS BiCFET clamp with a reasonable area has a leakage bottleneck of about 0.5 microamperes at 0.8 volts at 85 degrees Celsius. Also, we notice that the ESD performance of diodes is further reduced. For 65 nanometer up to 65 nanometer technology, we have diodes with current shunting ability of about 35 milliamperes per micron. However, if we go down to 28 nanometer or 16 nanometer technology, then we only have 20 milliamperes per micron current shunting ability. Consequently, diode parameter scaling is required to compensate for reduced performance. However, this leads to an increase in the capacitive loading. Let's now move on to traditional ESD approaches for I/Os. The traditional analog I/O protection scheme is the dual diode approach. This simple concept includes two diodes, one from VSS to the I/O pad and another from the I/O pad to VDD. This yields good characteristics like low leakage, low parasitic capacitance, and small area. However, it needs an efficient power or rail clamp. Practically, this means the distance between the I/O and the rail clamp is limited. In dual diode configuration, we have to consider the influence of the combination of the diode up, bus resistance, and power clamp. The total voltage drop over these three components must remain below the critical voltage to avoid damage in the I/O transistors. If we consider each item individually, this is the top part of the slide, we realize that they perform within spec and can withstand the required amount of ESD current. However, when we combine all three of them, we notice that it is not possible to withstand the required ESD current without exceeding the critical voltage. What this means is that a dual diode ESD protection scheme will damage the thin oxide transistors. An improvement on the dual diode scheme is the so-called secondary protection scheme. The secondary protection scheme involves extending the ESD design window by using an isolation resistance to limit the current and a small secondary clamp to limit the voltage over the gate oxide. We summarize the traditional analog I/O protection approaches. The dual diode approach has good characteristics, but leads to ESD level dependence on the bus resistance and is not efficient for situations where we have a narrow ESD design window. The secondary protection approach provides better protection for sensitive nodes, but is inappropriate for high-speed circuits since it uses a series resistance. There is a lot of room for improvement in order to obtain a solution suitable for high-speed circuits, which need effective protection without resistance, overvoltage tolerance, and low parasitic capacitance. So we now move on to the local ESD protection scheme. As we have seen, protection of high-speed IOs based on core transistors is not possible since self-protective devices and dual diode plus rail clamp options are not feasible. The solution is to use a local IO clamp. The local IO protection concept has many advantages when applied to high-speed circuits. The first advantage is a strong reduction in the voltage drop during ESD. This leads to effective protection for extremely sensitive nodes without an isolation resistance. The second advantage is the reduced dependence on the bus resistance. The third advantage of the local I/O protection scheme is the possibility to separately optimize each I/O interface. And the fourth and final advantage is that it allows for higher ESD thresholds and reduced parasitic capacitance. There are two main types of local I/O clamps we refer to in this presentation. These are the SOFIX proprietary ESD on SCR and the DT SCR. In both cases, the clamp device is a silicon-controlled rectifier. The diode-triggered silicon-controlled rectifier, or DT-SCR for short, is triggered once the chain of diodes at the G2 node is forward biased. The ESD on SCR clamp is triggered once the I/O voltage level is a forward diode drop higher than the supply voltage. Now that we have established that local ESD protection is a viable approach for high-speed circuits, we look at specific SerDes examples. The first example we look at is realized in 16 nanometer FinFET technology. So in this 16 nanometer FinFET technology project, we look at an ESD on SCR device, which is used to protect a circuit based on core transistors. Despite the very narrow ESD design window, we achieve more than 2.1 amperes of TLP. Because SCRs support a lot of ESD current with minimal junction area, the area and leakage are both small. The full local protection with ESD on SCR clamp protects 0.8 volt transistors. A frequency sweep evaluation is done to calculate the capacitance. Capacitive loading stays below 100 femtofarads. The conclusion is that this local clamp is suitable for 30 gigabits per second interfaces. The second example we look at is related to silicon photonics for high-speed optical communication. Optical links need custom ESD clamps because the controlling ASIC is still an electrical IC. They are based on advanced CMOS technology, and the ESD sensitive transistors still need adequate protection. At Sofix, we have worked with several silicon photonics projects on various processes. This range from the more mature technology nodes like TSMC 180 nanometer and 130 nanometer, down to more advanced nodes like 7 nanometer FinFET technology nodes. Our focus is on the protection of the CMOS ASIC. The main aim here is to protect high-speed interconnects. So these are the transmitters and receivers, as well as the low voltage thin oxide domains. We supported several silicon photonics projects on 28 nanometers. Here, we do not focus on regular low-speed IOs. Rather, our work focuses on 28 gigabits per second differential circuits with following characteristics. 1 volt IO with 0.9 volt tin oxide transistors, ultra-low parasitic capacitance with a maximum of 20 femtofarads of parasitic capacitance, ESD safe assembly with ESD level reduced to 200 volts HPM, and an ESD design window modified to shunt transient ESD current below 4 volts. Transient simulations reveal a voltage at the input pad during HBM stress. The foundry solution, shown here in green, and an approach using dual diode lead to transient voltage overshoot, which damages the functional input circuit. Only the local protection approach yields safe protection. Full local protection is achieved in both directions. So this means we have full local protection between the IO and VSS and between IO and VDD. A 1 volt power clamp is used for stress, a 1 volt power clamp for stress from VDD to VSS is integrated together with the local clamps. It is isolated from the substrate to reduce noise interference, and we have a small area and a low leakage current. The total ESD capacitance of less than 14 femtofarads consists of parasitic capacitance of the junctions and metal connections connected to the IO pad. This plot shows the capacitance across DC bias at input. The rule of thumb to reduce capacitance from metal connections is as follows. Work vertically. Remove wires where possible. Reduce metal 1 as much as possible and keep it on top of the diffusion. The final example we look at is realized in TSMC 7 nanometer FinFET. So this is another silicon photonics project, and here we deliver several clamp versions. The first one is a 2 kV HBM version for regular IOs exposed outside of the assembly. The second version is targeted at 400 volts HBM for high-speed die-to-die interfaces with a total parasitic capacitance of 50 femtofarads. The final version is a smaller one targeted at 150 volts HBM for high-speed die-to-die interfaces with a total parasitic capacitance of 15 femtofarads. We now move on to the conclusion. In this presentation, we first talked about the problem. Conventional dual diode ESD protection is not good enough for high-speed SerDes on advanced CMOS and FinFET nodes. The total voltage drop exceeds the failure voltage. We then presented our solution. We used local ESD protection in the I/O pad. We supported several projects based on our proprietary diode-triggered SCR and ESD on SCR devices. The local clamp reduces the dependence of the bus resistance and clamping voltage. Each analog I/O is optimized separately. In this talk, we presented case studies for local ESD protection with the following characteristics: low parasitic capacitance, small silicon footprint, and low leakage. The examples in this presentation are based on dedicated ESD test chips on 28 nanometer CMOS and 16 nanometer and 7 nanometer FinFET nodes. Our solutions are silicon proven, used by more than 20 companies, and we have more than 10 projects on silicon photonics and protection of high-speed SerDes interfaces up to speeds of 112 gigabits per second. Thank you for following this presentation, and please feel free to get back in touch with us in case you have questions.